Hi everyone. For this first video in our week 6 series, we're going to be talking about more hypothesis testing. And this week we're going to be talking about testing claims about categorical variables. And in order to do that, we're going to use a new distribution called the chi-square distribution. So far, we've performed inference on means, where we use the standard normal, or the student t-distribution. And we determined which distribution to use based on whether the population standard deviation was known or not. If the population standard deviation was known, we used z, and if it was unknown, we used t. We were also making the assumption that either our sample size was bigger than 30 or our underlying population was normally distributed per the central limit theorem that we learned about way back in week 3. When performing inference on proportions, we used the standard normal distribution with some limitations. We were approximating a discrete binomial. Because proportions are inherently binomial, we're dealing with things that are either a yes or a no, a success or a failure. And in order to approximate a discrete distribution with a continuous one, we needed to meet the large counts condition, which was n times p is greater than or equal to 10 or 5, depending on whose textbook you're looking at, and n times q is greater than or equal to 10 or 5, depending on which textbook you're using. And that ensured that our sample size was large enough and that we had enough successes and failures that we could approximate a discrete distribution with a continuous normal distribution. For performing tests on categorical variables, we're going to be looking at two-way tables full of frequencies or counts. And in order to perform these tests, we're going to need to use a new distribution. We're going to be looking at several different things. For example, we can test claims about whether two things are related, whether one variable is independent of another, whether two distributions of continuous or rather categorical variables match or not. And we're going to look at all of those tests, all of which depend on a chi-square distribution. You can see a graph of the chi distribution on the right side of this slide, and you'll notice, much like our student t distribution, it is a family of curves. And it is a family of curves that is going to depend on a degrees of freedom, just like the student t did. But there are a couple of important differences. First, I know that the t distribution, much like the z distribution, is symmetric. The graph that we're looking at here is clearly not. So let's take a closer look at this new distribution and some of its important properties. So the first is it is a family of curves that depends on the degrees of freedom k. The second is that it is right skewed, meaning the peak is on the left and it has a long tail on the right. The smaller the degrees of freedom, the more that skewness is pronounced. As our k gets larger, that peak shifts further out from the origin and more towards the center of the distribution. The mean of the distribution is equal to that degrees of freedom. That also means the mean is to the right of the median. We know the median should be pretty close to the peak. That mean of k is going to be to the right of the peak. The standard deviation of this distribution is the square root of 2 times its degrees of freedom. As k increases, the curve is going to become less skewed and more symmetric. And for a degrees of freedom greater than 90, the curve approximates the normal curve. So for very, very large samples, the chi-square distribution is going to look very similar to the normal curve. And we can see here, this is a picture of the chi-square distribution for a degrees of freedom of 100. And it looks like a bell-shaped normal curve with a mean at 100. It turns out that we can calculate probability and x values for the chi-square distribution just like we've been doing for z and t. On your TI-84 calculator, we can calculate probability for the chi-square distribution, meaning I can find p-values manually if I need to, by using the chi-square CDF function. A note, if we go back to a previous slide and we look at the original distribution, come on. There we go. We can see that this graph starts at 0, even for k equal 1, which is our smallest degrees of freedom. So this should never have a lower bound less than 0. Oops, I went too far back. There we go. So if we're finding a p-value by finding the area in a tail, that lower bound should never be negative. The smallest possible value is 0. The downside to the TI-84 is it can't calculate x values, meaning if I know the area, I can't work backwards to figure out the boundary value. The upside is we don't really need to do this for these tests because the tests are built into the calculator, so I won't need to do these individual steps. The GeoGebra statistics package is a little bit more robust. You can calculate the area in a tail using the chi-square command. It is going to assume that the lower boundary is 0, and it only asks you for a degrees of freedom and an upper bound, meaning it is always finding a left tail. And you can calculate chi-squared using inverse chi-squared. It is also going to assume that the probability you feed it is a left tail. So that's it about the chi-square distribution. When I see you in our next video, we're going to start looking at one of the 3 specific tests that we can perform for categorical variables. If you have any questions on anything you saw or anything posted in Canvas, feel free to contact me via email or drop by office hours. Otherwise, I'll see you in our next video.